Thanks for having me. It's really great to be here at Google. I'm always curious as to what Google is up to, so maybe I get to ask you guys questions after the talk. It's about this detection that I want to talk today. I don't know if people heard on February 11th, 2016, just this year, there was an announcement made about an otherwise very obscure experiment nobody had heard of before. And suddenly it was on the cover of all the newspapers internationally. It was reported everywhere, radio and television, that this obscure experiment had announced the discovery of the century, the first human-procured recordings of gravitational waves. Did you hear this? And gravitational waves were cited as ripples in the shape of space-time. That's what everyone always says. They're ripples in the shape of space-time. They're literally a squeezing and stretching of space. The recording that was captured was of the collision of two black holes that rang the space and time around them, like mallets on a drum, ringing the drum of space-time. Those waves in the shape of space emanated out, traveling at the speed of light, although they are not light, which I think is a very important distinction I'll try to emphasize. And they took a 1.3 billion year journey before sloshing over the Earth and striking this experiment. Did you hear the gravitational waves? Okay, we're going to listen to them anyway. Ooh, that's loud. That's good. Loud was good. That's okay. So that sound was not so loud. They were actually listening to the detector in the control room when this struck, and it was too quiet to hear. It would actually probably have been loud enough to hear by the human ear through the speaker system in the control room, but it happened so fast that the operators in the control room couldn't have parsed it, really. It happened too fast. But I want to discuss why we're talking about this as sound, really. That's the part I want to emphasize. I know people have heard this, they've heard the recording, they saw the discovery in the papers, but I think that people are still quite unsure what it all means, why it's a sound, why it isn't a picture, and what this discovery means. So that's kind of what I want to pick apart today before we do the Q&A. Here is the universe sort of as we know it. This is from the Sloan Digital Sky Survey. Every object in this survey has been observed. This is not a cartoon. These are real observations. Those objects are all galaxies. So each galaxy has 100 billion stars or more, and there are 100 billion galaxies in the observable universe, as many galaxies as there are stars in the Milky Way. And it just goes on and on forever, every one of these being an entire galaxy. Now, so much of what we know about the universe, almost everything that we know about the universe, comes to us from light, from things like telescopes, right? We sit on this planet for the most part. Occasionally we put something in orbit around the Earth or the sun. But we just, from the confines of this rocky planet, basically, we collect light and take pictures of the sky. And we've amassed this incredible story that the universe is 13.8 billion years old, that it's full of galaxies, that we are not at the center of the universe, that the universe expands, that there was a Big Bang 13.8 billion years ago. We know that there are black holes, maybe hundreds of thousands, maybe millions in every galaxy. We think there are supermassive black holes, millions or billions of times the mass of the sun, in the centers of these galaxies. We know that there's dark matter, matter that we can't see, but we only indirectly see its effects, and dark energy. But what else is out there is sort of the question. If we know that there's dark matter and dark energy, are there other dark things that we simply can't see? And black holes are an example of dark things that usually we can't see. So here is an astronomical image. Again, this is not a cartoon. This is a real image of a galaxy in the direction of Hercules, the constellation Hercules. It's an entire galaxy, hundreds of billions of stars. It's actually a very big galaxy. It's bigger than that. In the center is a supermassive black hole, we suspect. And why do we suspect it? Because we see these huge jets coming out of the galaxy that are powered by material being taken down by the black hole and spat out before it falls in. People often ask me, how did the material get out from inside the black hole? Nothing can escape a black hole. It doesn't come from inside the black hole. It actually never makes it inside. It gets shot out along these tremendous jets, and those jets are millions of light years across. And we see them from this great distance, and that's how we figured out black holes are out there. But essentially, black holes should be invisible to us. Usually. So there's lots of black holes out there that we simply couldn't see, that are too dark to possibly see. And that's where the gravitational waves come in. So gravitational waves are a way of observing the universe, but not through light. The Gravitational Wave Observatory that made that discovery is not a telescope of any kind. It doesn't take pictures of the sky. It actually makes a recording of the ringing of the shape of space-time. So you want to try to get into that stuff? So let's try to get into that stuff. It was interesting that all of this does come from Einstein's theory. So a lot of people were saying very excitedly, this was the confirmation of Einstein's theory of relativity, but nobody was that surprised about this particular confirmation. In some sense, it was much more the fact that it could even be done at all. So here's an example of space-time. You know, if we're in the space of this room, we don't see curves in space-time. This is Einstein's theory. Einstein's theory is that space-time is curved in response to mass and energy, but we can't see these curves. If you were to float in empty space and you were to throw objects in empty space, they would trace straight lines, right? If you're an astronaut and you're far from the Earth and you can't see any stars, and you were to just throw, I don't know, what do astronauts have their hands on? I don't know, a bolt, something, a tool, it would travel in a straight line. Right? So if I imagined painting those curves in space-time, I would imagine painting a straight line grid. Okay? This is a way to give you an explanation of what curved space-time, an intuition for what it's like. Einstein's theory says, if I put a big mass in that space-time, like a star, it will curve the shape of space around it. And you already know that to be true. If I take this clicker and I throw it, you know it's not going to travel in a straight line. Right? It's definitely going to trace an arc and fall to the Earth. And if we could paint all the paths that I could imagine of throwing probes, you could actually paint the curved space-time around it. And so intuitively, it seems like such a huge leap, but yet intuitively we all know it's true. We live in a space-time where things do not travel on straight lines. And those paths that things travel along, when they're free and weightless, like this would be if I let it drop, or like it would be if I threw it, those are the curves in space-time. So when Einstein proposes this theory, it takes him forever. He really struggles with the mathematics of general relativity. But when he comes up with the theory, the first thing he turns to is the topic of gravitational waves. And here's the reason why. If space-time is curved by heavy masses, then if those masses move, the curves have to move and adjust to follow it around. Surely, if the sun were to go halfway across the universe, the curves it creates around it must also move. And those are the gravitational waves. What happens is the curves in space actually have to move and adjust slower than the speed of light, or at the speed of light in this case, because no information, not even gravitational information, can go faster than the speed of light. So these waves curve and adjust and follow the mass and then wave outward throughout space-time. Now, Einstein many times said gravitational waves are real, they're not real, they're real, they're not real. Over decades, he was changing his mind and writing different papers. Sometimes he would write a paper that said gravitational waves are not real, and between acceptance of the paper for publication and print, he would write it saying, which one did I say? Not? That they are. Okay, so he changed his mind many times. This is not simple stuff. So this is from 1915 to 1916. In the 30s, people are still arguing if gravitational waves are real. In some people, even in the 60s. In the early 70s, very visionary people like Kip Thorne start to become convinced that gravitational waves are real, and that somehow they're fundamental to our whole theory of gravity hanging together. This is a computer simulation, now modern times, of two black holes colliding. And it's a very formal mathematical system based in relativity. This problem, even on a computer, since you guys like to code a lot, will appreciate was so hard. Even though we know Einstein's theory of curved spacetime, we can write the equations down, we can plug them into a computer, it doesn't just run. It was a numerical problem that seemed insoluble. And that's because gravity is very nonlinear. As a spacetime would curve and change with the two black holes, it would feed back into itself in such a complicated way that they couldn't get the codes to run. It took 30 years, 3 decades, for them to write the codes properly and solve that numerical problem. So here is a beautiful visualization of that, one of the numerical solutions. It shows two black holes. They've helpfully painted the curves in space-time around it, kind of contours. If you can see the red coming out, those are the gravitational waves emitting as two black holes bang on the drum, ringing space-time, sending the waves outward at the speed of light. The two black holes collide. They make a bigger black hole, which just settles down to this perfect shape and goes quiet. And that's the prediction. This prediction is already, this must be many years old, this simulation, maybe 10 years old. And it's an incredibly accurate prediction of what the gravitational waves would sound like. They would travel through the universe, getting quieter and quieter until it hit the Earth. This is, I'm going to show you a much less sophisticated simulation that's based more in analytical calculations. I'm going to show you the orbits of two black holes. I'm not going to show the contours of the space, but we're going to listen to them. Okay, so this is what it would sound like if you could record the ringing shape of the drum. So one of the black hole paths is yellow, one is red, and they're going to start to spiral in together. So these two black holes are equal in mass, which is why they're both moving. One's not heavier than the other, so they're both whirling around. And as they get closer together, you can hear the frequency goes up. And eventually they're going to merge. So you heard that chirp, and that's a lot like the chirp in the actual signal. You see how similar? That's what's called the chirp, is when it sweeps up in frequency as they collide. Now, even now, you sort of maybe have a better intuition of what the waves are, but why are they sound? If you were an astronaut floating nearby those two black holes colliding, you would not be able to see them, but it could ring your eardrum. I mean, I always say that I'm not, I don't know anatomy that well. So I have talked to people who study the ear in detail, and they say it's plausible. You know, I've never tried to do the experiment floating near a black hole. But if you heard that, you'd like want to get out of there. If you're floating near darkness and you hear this chirping up, it's like time to scoot. So technically, it is very much like sound. It's not just a weak analogy. You know, I can take any kind of light waves and translate them into sound. That's not what's happening. This is not light. It's literally vibrations on the drum, and so it's like almost like having an electric guitar where you pluck the string and it makes no sound until you amplify it, right? Until you record the shape of the string and you amplify it. That's kind of what this instrument does. It records the shape of the ringing drum. We'll talk about that more, and it plays it back as sound. Here's another pair of black holes. One is much heavier, so its orbit is in yellow. It hardly moves because it's 10 times heavier than the other. The other moves much more. You can see the orbits of black holes are pretty crazy. They're not like solar system orbits. When they get close together, they get pretty wild. And you can hear the difference between this one and the previous one. Hear how it gets quiet and then louder? So we can hear that the whole system's moving like this. We can hear that they're not on circular orbits. And we can even hear that they're spinning if you know how to listen. Okay, and then they merged. But it still chirps. That chirp is a real characteristic of all these black hole systems. Sorry, did I touch the volume? Okay, wait, before I do that, let me go back for a second. At the time that people decided to build this instrument, LIGO, so the experiment, this obscure experiment no one had ever heard of that made this detection, is called LIGO. It's the Laser Interferometer Gravitational Wave Observatory. It actually made the detection in September 14th, 2015. They didn't announce it until February, but it made the detection in September. This experiment was dreamed up in the late 60s, and it sort of started to spread. Different ideas were spreading about trying to do something like this. But one of the original architects was Rai Weiss. He was a young professor at MIT. He didn't understand the general theory of relativity. He was trying to teach it because MIT said, "You're running a gravity research program, you should teach general relativity." And he says, "I couldn't tell them I didn't know general relativity," right? So he starts to teach this class. He says, "I was bumbling, but the students didn't walk out." And the reason they didn't walk out is because he was dreaming up ways to actually do experiments with the theory. And that's when he dreamt up this idea. Look, if there are gravitational waves, he thought, and they come across the Earth, then things will bob on the wave by the time they get here. If I could suspend mirrors very delicately, they would sort of bob as the wave passed. And if I could keep track of the distance between those mirrors, I would know if they had moved slightly apart and in, and I could record the shape of the ringing drum. So if you could had extremely accurate clocks, you would be able to do that with what we call just one arm, just two mirrors in a vacuum so the laser light doesn't get scattered, and shine the laser light between the mirrors, and with a very precise clock, you could keep track of where those mirrors are. We don't have such precise clocks, so instead he thinks of an interferometer, which is two arms in an L shape, and you'll see the LIGO instruments in a second. And the light comes back and goes down the two arms and comes back, and if it traveled the same distance in both directions, then the light would interfere perfectly, and if it traveled different distances, then it would interfere imperfectly, and the waves would create what's called a fringe pattern. And so it's a much simpler detection to look at the fringe pattern than it is to try to use a clock. And he started building this machine. It was 1.5 meters. He was building in a place called the Plywood Palace. It was this ramshackle structure that was thrown up during World War II, and it was supposed to be torn down, and they didn't tear it down. It's supposed to last for 10 years. It wasn't torn down for another 50 years. And they used to punch holes in the ceiling and break the pipes, and they would literally perform experiments and go right through several stories, and it was a crazy place. 9 Nobel Prizes came out of the Plywood Palace. And it was almost the crappiness of the structure that allowed them, right, to just be free to experiment. He describes that when he began these experiments, everybody thought he was crazy. First of all, they said, it will never work. Technologically, it's impossible what you're trying to do, because by the time the gravitational waves get here, their variations in distance that we expect it to affect is a billionth of a trillionth of the length of your machine. Okay? A billionth of a trillionth of the length of your machine. So a 1.5 meter machine isn't going to get anything. One of his colleagues from MIT said, you couldn't even record the sun exploding. I could look out the window and do better, And eventually he ran out of funding, his grants were turned down, and then he found out after he had been declined from his grants and people started telling him, you're not going to get tenure and you're not going to succeed, he found out that a German group, which had read his grant to review it for the National Science Foundation, had started to build these instruments, but bigger and better. Okay? So there he is in this ramshackle structure with no money. People are against him. They don't even believe gravitational waves are real. They certainly don't think black holes are real at this stage in time. And he's about to lose out. Right? He's about to lose out. And he says, then what happened is I met Kip Thorne. Kip Thorne is the iconic astrophysicist from your part of the world. He's a Caltech professor, very theoretical, very brilliant man. And they go on this campaign together. Okay? So skipping ahead a bit, 50 years later, 800 people invested in the experiment, nearly $1 billion. 2 instruments that each span 4 kilometers make the detection of the century. And it's not an easy 50 years. It's an arduous 50 years. Here is the full-scale detector. This is an instrument in Hanford. These are the arms. The mirrors are suspended at the ends of these arms, and the laser light travels along those vacuums. That's the site in Louisiana, and you can tell because it's swampy. There are alligators and bass and things like that in the swamps. So here we're going to see the laser light. This part is a cartoon, obviously. You can't go inside the beam. But that vacuum, wasn't built until 1998. It has stayed in a vacuum. It's two of the largest holes in the Earth's atmosphere ever made. And these are the chambers at the corner stations where the mirrors are and the beam splitters and all of the optical components, but the rest of it's just vacuum and laser light. So if that vacuum is broken, one of the head's lead scientists told me we'd all go home. It would all be over. A lot of the expense is in keeping that vacuum alive or building it in the first place. There's the physical difference between the two sites, and they put them far apart so that there's not the possibility of coincident false alarms. And they're basically recording devices. So imagine some ripple in the shape of space comes from far away, it rings the instruments, they record it, and they literally play it back as sound in the control room. You can listen to the detector in the control room, and it's constantly noisy and humming. They hear earthquakes in China, they hear winds from the Gulf, they have all kinds of seismic activity. Planes, the moon, the sun, tides, everything rings this machine. It's very noisy. But the billionth of a trillionth of an arm, a 4-kilometer arm, amounts to tiny variations in distance less than a 10,000th of the width of a proton. And that's what they recorded, which is quite remarkable. This is the sound of the instrument in the control room. This is the noise. This is what it sounds like most of the time. You can hear different modes in that. Okay, so this is what happened. On September 14th, Ray himself, 50 years later, is still at the sites working on the machine. He was there on September 13th looking for radio interference, and they were not ready to run detections. The machines were operational, they were ready, but some of the algorithms weren't ready for the data analysis, and they were still doing what they call an engineering run, which is you run tests and you interrupt the machine and you see how it responds to certain vibrations, trucks braking, banging on it with hammers, whatever they're doing. Ray, luckily, his wife says, come home. So he puts down his tools and he goes home. In the middle of the night on September 14th in Louisiana, in the middle of the night in Hanford, Washington, where the other instrument is, the young scientists, the people working on the sites and the graduate students, they're running their tests, they're taking the machine on and offline, they finally decide they've had enough, it's too late, and they go home. 4:50 a.m., coming from the southern sky after a 1.3 billion year journey, within a span of an hour of them leaving the instrument in observing mode, it strikes Louisiana. 10 milliseconds later, maybe a little less, it cruises across the continent and rings the Hanford machine. And it's this spectacularly loud, beautiful event. And this is what it was. If you pointed a telescope, this is a computer simulation, not a picture, not a movie. We couldn't possibly see it with a telescope, but this is what it would look like if you could look at the lensing of the light behind the two black holes. One was about 29 times the mass of the sun, one was 36, I think. They're pretty big black holes. They're orbiting each other in the final seconds of their life together. This is vastly slowed down. They're going at a half to 0.7 of the speed of light. Do you guys want to see that again? It's pretty great. Let's see that again. They're going about a half the speed of light up to almost 0.7 the speed of light, like 70% of the speed of light. They're about 200 kilometers across, roughly, in size. And all we caught was the last 4 orbits. That was the only part that was loud enough to detect. The event horizons are empty space. These are just holes in space-time. The event horizons touch and coalesce and make a bigger black hole. You can see how deformed it looks. And eventually, that bigger black hole rings down and becomes quiet. And we'll hear it again in a second. So look, it's quite spectacular how distorted they start to look, and then they wobble together and they form one quiet, spinning black hole. You can't even tell that black hole spinning. So here's what happened at the observatories 1.3 billion years later. So that's what they hear. And again, it's slowed down. They only hear it once, of course. It's just for effect that they like to repeat it. They had 200 milliseconds, a fifth of a second. So you got to play it 4 times to get any kind of feeling out of it. So it took them months to analyze the data, but that morning in Europe, people wake up and they see this candidate event in the data, and there starts to become a lot of chatter. People start talking about it. People wake up eventually 8 a.m., a few hours after it happened on the East Coast, and eventually in Hanford, and they start to hear all this chatter, and everyone's incredulous. Somebody said, we just turned the thing on. There's no way. People told me it wouldn't be until 2018 that the first detection was made, and everybody told me it wouldn't be black holes, except for Kip Thorne. Okay? Kip always said it's going to be black holes first. And Rana, who's one of the experimentalists, said, this time we're going to detect something. And I said, Rana, how can you be so sure? And he said, I always say that. I say that every run. And he said he didn't even look at the data for a day because he was so incredulous. He thought, this is ridiculous, it's not real. And they worried that it had been intentionally injected into the data as a false signal, which is something that the experimentalists do on purpose to test the experiment. They inject false signals into the data. So everyone thought, oh, God, it's a blind injection. This is ridiculous. Mike Landry, lead scientist at Hanford, said he sat down that morning. He was kind of pissed off at the team of injectors. He's like, what are you guys doing? We're not ready for this yet. He sits down next to the guy and says, are we in a phase of blind injection? The guy goes like, no. And he starts to ask, he's not allowed to ask, did you do a blind injection of 2 black holes colliding? But he can sort of ask, are we in a phase? And he permutes the question until a few times, and he keeps getting no, and finally he says, are we in a phase of injections of any kind, anywhere? And the guy says, no. And he says, I got cold, is what he told me. He said, I just went cold. So on the telecom that day, everyone's talking, and many people are raising the possibility that it's a blind injection, and somewhere in the phone call, Mike says, I don't know how many people are on the line, many, many voices on the line. This is an 800-person international collaboration. Mike says it's not a blind injection. Someone else says, sorry, Mike, can you say that again? And that's when they started to take it seriously, which is pretty remarkable, pretty fortunate that it just shows that quitting and going home can be a very effective technique. So here, just to wrap up, is another view of our universe. Again, this is not a cartoon. This is real data from the Hubble. Everything you're seeing here is an entire galaxy. And again, we can see a lot in the universe, but we know that all the light that we receive, that the constituents of the universe that are luminous is less than 5% of what the universe has in it. Everything else is dark energy, dark matter. Among that 5%, black holes are actually part of that small 5%, but it just means that the universe is a vast amount of dark phenomena that we will never see with telescopes, that we could only hope to record with something like a gravitational wave observatory. So as the universe expands and eventually gets darker, the universe will also go quiet. But in the meantime, what we're really hoping for from these experiments is that they'll detect things we haven't even thought of before. Not just black holes, colliding neutron stars, supernova. These are all game for the gravitational wave observatories. Neutron stars are stars that didn't quite become black holes, that died and collapsed but couldn't form black holes. We expect to be able to record a whole range, as long as it's kind of cataclysmic, big astrophysical phenomena. But I think the real hope is that we'll detect something we've never even thought of before. Okay, thank you. I'd love to take questions if people want. Hi.
Hi there. I was curious how you were able to locate the event in 3-dimensional space with 2 interferometers.
It's not easy. So I always liken this to listening for your phone. If you don't know where your phone is and it's ringing and you can't see it, it's really hard to find your phone. So you need 2 ears for any kind of location ability, and 2 interferometers helps. If you only had 1, you would be saying it's kind of from over there, like a whole huge patch of the sky. With 2, you can do better. but it's not great. And so the future is expecting many more interferometers, a whole network on the Earth, that there's going to be an underground instrument built in Japan. There's one in Italy that's almost online. It's not as sensitive, but it will really help with location. There might be one in India, which is going forward. So, so that's going to help a lot. Yes. Hi.
Hi. So many questions, I don't know where to begin. Let me ask this one. We know electromagnetic radiation attenuates with distance.
Yes.
Is that true of gravitational waves as well?
Yeah, it gets quieter with distance. So the closer you are, the louder the event would be, definitely. And also, I should point out that this was the most powerful event we've had since the Big Bang, that we've detected since the Big Bang. The power that came out was many billions and trillions of times the power that comes out of the sun and light. So this is an incredibly powerful event, yet it's very quiet. So if you blew up a nuclear bomb, you would not be able to measure the gravitational waves from it. It would be totally insignificant. Yes.
So you got this event within a few hours of turning the instrument on, and now it's been on for half a year. Have you gotten many more?
Okay, well, I have to clarify that I'm a totally theoretical physicist. So I don't build the machine. And part of what happened is that I started following so closely this experiment out of fascination, because it was other. I do a lot of theoretical work about the colliding black holes and the predictions, but the idea that anybody would take it seriously enough to try to build a machine just seemed ridiculous to me, you know? And so I am technically not supposed to be privy to the detections. They did tell me, though. I think I was the only person that was officially told of the detection before the formal announcement on February 11th. And I can tell you that in that February 11th announcement, they did talk about another bump, right? Another signal that looks like, sounds like two colliding black holes, but it was nowhere near loud enough or significant enough for them to have made a claim of a first detection with that. It came later, but it was significant enough that it's helping them assess how often this happens. And so it looks like there's going to be a lot of black hole collisions. And the machine is down right now. It's been down since January. It was not at advanced capability. It was better than the previous generations of machines, but that's also why nobody really expected it to do anything right away. It still needs to become more sensitive by at least a factor of 3 or 4. So they take it down and they tweak it and they work on it, and they're going to bring it back up probably late summer. And when we expect, yes, we fully expect, maybe monthly, we're going to be hearing things like black hole collisions. We don't know if we're going to hear anything else. Yes?
Sort of related to the attenuation question, so if you take a bowl of water and you tap it, you'll see waves and they will still after a little while. So is there a analog of viscosity in space-time?
Not really. It's interesting, nor for light. So we still receive light from the Big Bang that's been traveling to us for 13.8 billion years. It's colder, right? It's redder than when it was created. That has to do with the expansion of the universe. But light never tires. Right? Light never slows down like what you're describing, and there's no friction, okay? And in the same way, there's really not for gravitational waves. They travel at the speed of light, and they also never tire or slow down. It's a way, we say that all particles that are massless travel at the speed of light. So you know the wave-particle duality. For light waves, there's a quantum particle called the photon, and as long as that photon is massless, it will travel at the speed of light. If it has any mass, then yes, it will slow down and stop. And the graviton, which is the particle analog or the particle complement to the gravitational wave, is massless as far as we understand. If it does have some small mass and we're wrong about that, then maybe they would eventually slow down and stop. And they would not be traveling at the speed of light. Any other questions? Oh, please.
Just a quick follow-on.
Come up to the microphone.
A quick follow-on to that.
Yeah.
We've not detected anything like a graviton, right?
No, it's way too hard. So gravity is so weak, we're nowhere near the regime of probing the quantum scale.
What would I mean, we kind of understand the, photon, how waves, electromagnetic waves and photons, can be, converted, back and forth between each other. Theoretically, what would the gravitational wave that they detected look like for gravitons?
You mean if we could probe the quantum level, or?
Yeah.
So the light in this room is made up of so many photons that it's really hard to notice the particulate nature of it. And similarly, the gravitational waves are made up of so many gravitons that it's impossible to notice the particulate nature of it. We haven't really very well thought of an experiment where we could do that. And probably the energy scale you'd have to get to is something like, let's see, 1,000,000 times the Large Hadron Collider energy, something like that. So it's not an ambition of the near future. I mean, this was pretty crazy, but that would be really crazy. Yes.
So it sounded like, I'm not sure if I understood correctly, but part of the reason your software was able to detect this event and notify you guys, because you kind of knew what you were listening for, you kind of had a prediction for what it would sound like? Is that correct?
Well, that is correct. One of the difficulties in this experiment is that the sound will often be quieter than the noise, and so they'll have to sometimes run the predictions, especially the numerical ones, in through the data and filter it that way and pluck it out. But this one was so loud, it's just right above the noise. It's actually really loud. Oh. So it's not as reliant on that as we fully expected things to be.
So is it that you guys are actually just running straight up anomaly detection, and that's what you want to use to like possibly detect other events in the future?
Yeah, there's 3 or 4 different teams within the collaboration that use different models to pluck out different kinds of signals. Some are burst signals, some are these what we call compact binary coalescence, things like black holes and neutron stars and white dwarfs, and some stochastic, which is just noisier. So there's all of these different algorithms that people write, but I don't think anyone expected the first signal we detect to be just noticeably loud. Yeah.
Thank you.
Sure. It was just fast. If it had been slower, I think they would have heard it in the control room. It was that loud.
What is the range of events that you expect to be able to detect with LIGO? I understand there are potentially like solar system scale interferometers for detecting more, less energetic events or more energetic events.
Right. So the scale. So it happens that LIGO is sensitive to the human auditory range, and that's just strange coincidence. But these black holes about this size, that's the natural frequency at which they would emit gravitational waves. But I think when they designed the instrument, this has been going on for 50 years, they were looking for supernova. They were hoping to hear things like that. So it turns out that the supernova might be too quiet or too difficult, and that these are much more populous. And so, but yes, if you sent something in space, and there is a project to send something into space, millions of kilometers apart, they would be way outside of the human auditory range, way lower in frequency, and they would be detecting things like supermassive black holes colliding, bigger things, and lower frequency stuff. Yes?
Hi. How close would we have had to have been to the colliding black holes for them to kill us with the gravitational waves?
That's an interesting question. It would be pretty hard to kill us with gravitational waves. They're so weak. It would be really hard, to be squeezed and stretched, like with your bare hands, you could squeeze and stretch me billions of trillions of times harder than a gravitational wave could. So I think I'd be much more worried just about being near the black holes generally. So, but black holes aren't really the engines of destruction that they're portrayed to be. If our sun was replaced with a black hole tomorrow, we wouldn't get sucked in like a vacuum cleaner would suck us in. We would actually orbit just fine. The orbit would be exactly the same. It would be totally fine. I mean, we'd be dead because it would be cold and dark. But we wouldn't fall in. And we were actually very slowly falling into a black hole now. There's a supermassive black hole at the center of our galaxy, 4 million times the mass of the sun, and we are in fact falling into that black hole. It's going to take a very long time. Very long time. I really am worried about other things. Yeah.
If you had an infinitely sensitive detector, where would you see gravitational waves from? Would it be from everything, or is it just...
Everything. I would make gravitational waves right now. Okay. Infinitely sensitive detector would pick up gravitational waves from all of us moving around. And
you have to be moving.
You have to be moving. So a black hole just sitting there is not going to create gravitational waves. And it's just a funny thing that if like a star exploded perfectly symmetrically in all directions, it actually would not create gravitational waves. So you need what's called a quadrupolar, or a certain kind of asymmetry and accelerations of masses. Yeah, but I'm not spherically symmetric. So I am making gravitational waves.
Yeah, about the one that have been detected, I'm curious about what we can know about them, their relative size.
The black holes, you mean?
Yeah, the one that we have.
Yeah.
Sound. What can we know about them?
Yeah, it's pretty amazing. So the details that we seem to be able to extract is one was about 29 times the mass of the sun to begin with. One was over 30. By the time they collided, they made a black hole maybe about 62 times the mass of the sun, which means some of the energy that we call E equals mc squared energy was emitted in the gravitational waves. A few % of the energy was emitted in the gravitational waves. And that's a tremendous amount of energy. It's just a huge amount of energy. And that black hole is out there right now spinning. They think they know it's spinning very rapidly, probably hundreds of times a second. We saw the last 4 orbits or so.
So, but that, we know the location now of this black hole?
Not very well.
Okay.
Not very well. It came from the
know
southern sky.
Where?
It's somewhere over there. They have a map, a kind of splotchy map. It sort of came from over there. It's 1.3 billion years away.
Trying to find it?
They can't find it anymore because a telescope can't see a dark object. And so what they could try to do is pinpoint the galaxy that it lives in.
Okay.
And then that would tell it how something about the galaxy might tell us something about the black holes. Very surprised that they were that big. That was something that surprised people. I wasn't particularly surprised. I work on this a lot, and I've never had a prejudice against big black holes. But a lot of people did. They just thought it'll be hard to make them. But the details of how to make black holes is so hard. I always thought we're probably not right about a lot of that stuff. So this was real astronomical information from the first detection. It wasn't just we recorded gravitational waves. It was we've discovered the first black hole system, and we've discovered the first collision of black holes, and we know things that we didn't know before.
Ooh.
Yeah, it's very cool. They were very lucky, very lucky. Yes.
What other like gravitational wave detection systems are coming online soon?
Yeah, so there is this one called COGRA, which is going to be underground, and that helps isolate it seismically, so that will be helpful. At some level, the experiments are limited just by quantum noise, that there's nothing you can do about quantum mechanics. You know, quantum fluctuations, if you've heard about Heisenberg uncertainty principle, makes it impossible in some regime. They're working on suppressing quantum effects, but eventually they'll hit some fundamental physical limit where the Heisenberg uncertainty principle says you can never precisely locate an object, and they'll be up against that limit with the mirrors, right? It doesn't exist in a precise enough location anymore, technically. So, but COGRA will help with seismic stuff, and so there's Virgo, which is in Italy, which will hopefully come online this summer as well. And then I mentioned the one in India, and there's GEO, and I can't remember all of the others right now. Tama, I think, is offline now. But there's a whole network of them. Eventually in space, that would be very exciting. Do you mean just gravitational wave, by the way, or any gravity experiments?
Gravity wave.
Yeah, so these are the ones. They're all of the LIGO variety except the spaceborne LISA, which would put 3 spacecraft disconnected millions of kilometers apart from each other, freely floating in space. If a gravitational wave passes, they all just bob and they keep track of each other with a laser. It's a really clever experiment. There are some people who are trying different ideas, again, going back to atomic clocks and timing experiments, but they're very new, so it would be interesting to see if anyone makes progress with that. I put the clock at, we're counting down 2-1, but I think we could take one more question if somebody wanted to. Yeah. Or 2 more. Yes.
So I was thinking about the earlier question about the gravity waves. So they were formed by the black holes. They came by, they were detected, and as they spread out, they get weaker and weaker, so they don't really dissipate because there's no friction. So what happens to them? They just keep going on?
Well, just imagine a light bulb. Up close is very bright, and far away it's very dim. And it's just because you're really intercepting less of it to some extent, right? You're up close, you're intercepting a whole lot of the light, but if it's very far away, you're getting very little of it. The rest went to other planets and other galaxies. And you know, the farther out it spreads, the less any small patch of sky is going to get, just like a light bulb.
But they would ultimately just keep going forever? Or?
Yeah.
Okay.
And if the universe is finite, they'll come back again eventually. They'll wrap around, and then they'll come back again. We'll hear it a second time, even quieter.
The picture of the wave showed a
Yeah.
vertical axis of frequency oscillating around 20 hertz, I noticed, for
Yeah.
the last 0.4 seconds.
Yeah.
Surely the two objects were actually orbiting much faster than that, right? So how does that relate to their actual orbital velocity?
It actually, 20 hertz, it also, so the gravitational wave is directly related to the orbital rate. So if you think about that, that's extremely fast, right? 20 hertz is really fast because you're talking about something 200 kilometers, traveling several hundred kilometers, and doing that orbit many times a second. So it's actually incredibly fast, okay? And so you are going near the speed of light to be able to hit that frequency. And that's how, there was a previous question about what sets the frequency. That's sort of one way to think about it. You know, how far is it going in an orbit, and how fast is it going, and that will set the frequency. The gravitational wave is twice the orbital frequency is the relationship. I think that's it. Thank you. Thanks very much.